We have been studying the hydrogen atom problem, which is essentially a two-body problem. There is a proton and an electron interacting with each other through a Coulomb potential. We also saw in the last class that this two-body problem can be reduced to the two different distinct one-body problems, one corresponding to the motion of the center of mass, which behaves like a free particle, and the other part which governs the motion of the relative positions of these two particles. That turns out to be equivalent to the motion of one particle in a central potential, in a spherically symmetric potential. So, so then we have already made substantial progress in our understanding of a behavior of a particle in a spherically symmetric potential, and we have proceeded by writing the wave function psi r theta phi. Bear in mind that these now refer to the relative separation between the proton and the electron, the relative position between these two, the coordinate r theta phi. And for a particle in a spherically symmetric potential, we saw that the problem gets decoupled into two parts, one for the angular part of the wave function, and the angular part of the wave function could be expressed in terms of these eigenvalues, eigenfunctions of the angular momentum operator YLM, and the radial part which was expressed in terms of a function g of r divided by r. So we had expressed the wave function in this form, and we had obtained an equation for g, which we shall come back to shortly. Let us first look at the normalization of this wave function. So the normalization of this wave function so the integral of this wave function, the mod square of it integrated over all volume, should be equal to unity. We are working in spherical polar coordinate system where the infinitesimal volume element dV, the infinitesimal volume element can be written as r square dr into d omega, where d omega is the infinitesimal solid angle. Let me also write down what d omega is. D omega is sine theta d theta d phi. So substituting this form for the wave function here, we get the normalization is equivalent to the condition that g r, the mod square of this, divided by r square into the mod of y lm theta phi squared into r square dr into d omega. This should be equal to 1. Now we know that the spherical harmonics, the YLM functions, are normalized with respect to this integral over solid angle. So this integral over all solid angle and of YLM mod squared, this gives us 1. So the normalization condition for this function g is that the integral of the mod square of g dr from 0 to infinity, the r square, 1 by r square cancels out with the r square here, this should be equal to 1. Now we saw in the last class that the function g, the equation which governs function g, is nothing but a one-dimensional Schrodinger equation. So you can interpret this as the Schrodinger equation for a particle, some fictitious particle, which is moving in one dimension in a potential which is somewhat different from the original potential. The original potential is V of r, but this fictitious one-dimensional particle, it is moving in a potential which has this extra bit, which you can classically interpret as the centrifugal, the potential which gives rise to the centrifugal force. So the corresponding one-dimensional problem, so you can think of G as a wave function for a particle in one dimension. The potential jumps to infinity at for negative r, and it has this form for r greater than or equal to 0. So the normalization condition for G is also exactly what you would expect if it were a one-dimensional wave function, because in one dimension the mod square of the wave function into dx or dr, the integral should be equal to 0. And this wave function is 0 for r less than 0. So this you can think of as the normalization condition in one dimension, which is minus infinity to infinity mod g square dr equal to 1, where g is 0 for r less than 0. So this is the normalization condition on this part of the radial part of the wave function g. So now with this normalization condition, so what let us go back to the equation which we have to still solve for this function g. So the equation we have to solve is this, and any solution which we obtain has to satisfy the normalization condition which we just wrote down, which is the constraint. So now let us go ahead and try to get solutions of this equation. Let us first, where V of r, we also know that we are looking at a particular case where V of r is the Coulomb potential, which we have also written down yesterday. So let us now write down this equation in a slightly different way and then proceed further. So the equation is d square dr square g minus 2m by h cross square, and then we have the potential. So this is the equation I am writing down. So we can put in the form of the potential. The potential is E square minus E square by 4 pi epsilon naught r, and here we have plus h cross square by 2m L plus 1 by r squared this is equal to minus 2m by h cross square E into G. So this is the equation we are solving. Let us use some symbols to denote all these coefficients, all these constant coefficients which appear here. So let us the energy we know is negative. We are dealing with negative values of energy. So let us first define W to be minus 2m E by h cross square. So W is now positive. So this whole thing over here is W. The second simplification is that 2m E square by h cross square 4 pi epsilon naught, let us call this k, and here 2m h cross square cancels out with this 2m h cross square, so we don't have to bother about this term. So now let us write down this equation once more. So this equation now becomes d square g dx square plus, there is overall plus sign here, plus k by r minus L plus 1 by r square G is equal to W into G. So this is the equation we have to deal with. Now for very large r, for very large values of r, the potential dies down. So for very large values of r, we have negative energy, and for very large values of r, the potential goes to 0. So you can think of it that for very large r, these values will all be insignificant, and for very large values of r, this equation reduces to this. This term will not be there. So we know the solution of this equation for very large values of r. Asymptotically, the solution should tend for r going to infinity. The solution will be g of r will be proportional to e to the power minus square root of w into r. There will be another solution which is e to the power plus square root of omega r, but that blows up as r goes to infinity, and it is quite obvious that the positive part will not satisfy this normalization condition, so that is ruled out. So I shall not bother to write it down. So asymptotically, the solution of this equation behaves like this at large r. So let us use this in this equation. So let us now look for a solution which looks like this. So let us express g of r as equal to some u of r into e to the power minus square root of omega into r. So we have to first calculate the double derivative of g and use it here, and then we can cancel out this e to the power minus square root of wr throughout. So let us first calculate the double derivative of g, which will arise here. So the first derivative of g, dg dr, will be equal to du dr e to the power minus square root of wr minus square root of w into the same thing. This is the first derivative, which here I am first differentiating this and then I differentiate this term. Let me now calculate the second derivative, d square g dr square, and this will give me the second derivative of this function e to the power minus square root of wr, and then I will have minus 2 times du dr into square root of w e to the power minus square root of wr. One of these terms will occur when I differentiate this, and the other one will occur when I differentiate this u over here. And I have one more term which will be plus w into u into e to the power minus square root of wr, which is nothing but w into g, the original function which we had. This whole thing is g. So now when we use this in this equation, so let me show you the equation. So we are going to use the double derivative of g written in terms of u and e to the power minus square root of wr. Here we see that the last term, this term over here, which is w into g, will cancel out with this term on the right hand side, and what we have left is the sum of these two terms and this whole thing over here. So the final equation in terms of this new function u is d square u dr square minus 2 square root of w du dr plus k by r minus L into L plus 1 by r square into u is equal to 0. Right. So this is the equation which we have to now solve. Now how do we go about solving this equation? One method is to look at a series solution of this equation. So let us try out a series solution for this equation over here. So the series solution means we expand u of r. We have already done it earlier in this course. We expand u of r as a function, a sum of powers of this variable r. So n goes from 0 to infinity, and we have c of n r to the power of s plus n. The variable s appears over here because the lowest power which we may get in this series expansion may not be r to the power of 0, and we have to first determine what this s is. That is the first part which we have to do, and then we have to see what the relation between these coefficients are. So there are two things which we have to do. So we proceed by putting this into this equation, working out the derivatives, and then equating them, which will give us some condition for s and some condition for these coefficients c. So let us do it. So the first term over here, so okay, let us first just take a look at it before starting on the algebra. This, the second derivative, suppose we use this, suppose we take some fixed value of n. So that will have r to the power of s plus n. Now the second derivative will have r to the power of s plus n minus 2. The term over here, which has got L and L into L plus 1 by r squared, that too will have r to the power of s plus n minus 2 because of this 1 by r squared. So the coefficients here and here can be combined. Similarly, the coefficients of this term, which is r plus s, s plus n to the minus 1, are the same, will be this combined with the coefficients of this term, which also will have a s plus n minus 1. Okay, so let me just combine all the coefficients straight away. So the coefficient of, so this term we can write, we can combine this term and write the whole thing together. So we have one sum n going from 0 to infinity. The second derivative is going to give me, the first derivative is going to be give me s plus n. When I differentiate r to the power of s plus n, I will get a factor of s plus n. If I differentiate it again, I will get s plus n minus 1, and then I have c, okay, this is going to be one of the coefficients which will appear from this. Here I am going to have a coefficient minus L into L plus 1. So I have minus L into L plus 1, this whole thing into C n r to the power of s plus n minus 2. So this is this term combined with this term. And for both of these terms, the same power of r appears with the nth coefficient. Now let us combine this term and write down the resultant. So I have one more term plus n going from 0 to infinity, and this will give me, let me write down this first. So this will give me k, this term here, and this will give me minus 2 square root of w. I have one derivative, so I get s plus n, this whole thing, into Cn r to the power of s plus n minus 1, this is equal to 0. So this differential equation, if I use this form for the solution, it gives me this relation amongst these two sums. Now the coefficient of any particular power of r should individually be equal to 0 in this whole thing. So let us equate the coefficients of some particular power of r. Okay, so the power of r should be the same, which tells us that the value of n which appears here should be 1 more than the value of n which appears here. Okay. So the value of n which appears here has to be 1 more than the value of here, so that we get the same power of r in both of these terms. So let us do that. Let us equate these coefficients for that. So this, if this is going to be n, then this will be n minus 1. Okay, so what this gives us is that Cn into s plus n, s plus n minus 1 minus L plus 1 plus C n minus 1 k minus 2 square root of w s plus n minus 1, this is equal to 0. So we are taking n here and n minus 1 here and equating them. They will have the same powers of r, and the coefficient of that power of r should be equal to 0. So this is the condition which it gives us. Let us simplify this a little more. So what this gives us is that Cn by Cn minus 1 is equal to, so I take this onto the right hand side and then divide throughout by Cn minus 1 and divide throughout by this coefficient over here. So what this is going to give us, I am going to get an extra minus sign when I take this on the right hand side. So that is can be compensated for by interchanging these two terms. So what that will give us is 2 square root of w s plus n minus 1. Then I have minus k, this divided by s plus n, s plus n minus 1 minus L plus 1. So this is the recursion relation. We still have to determine the value of s. Now we want C naught to be not equal to 0, because that is the first term. If C naught is 0, then all the higher terms are going to be 0. So C naught cannot be 0, but C minus 1 should be equal to 0, right, because the whole sum starts from 0 onwards. So C minus 1 has to be 0. So if C minus 1 has to be 0, it basically tells us that when n is equal to 0, this term over here has to be 0. So when n is equal to 0, this term over here, this is going to be C0. This term, if this term is 0, then C minus 1 is going to be 0. So if for n equal to 0, we should have the condition that S into S minus 1 minus L into L plus 1, this whole thing is going to be equal to 0. Now there are two solutions to this. The first solution is that S is equal to minus L, and the second solution is S is equal to L plus 1. So now the question arises, which of these two solutions is the right one? Now let us look at the two cases. If S is equal to minus L, then the first term in the expansion of UR is going to be equal to, the first term is going to be R to the power of minus L plus, then we will have higher powers of R. But if we have R to the power of minus L, this diverges. As R tends to 0. And it will not satisfy this normalization condition that the integral g square r dr should be equal to 1. So this is ruled out. So this is not the right, so this is ruled out. So the correct solution is that S is equal to L plus 1 is. So this is the correct solution. So what does the recursion relation finally stand to? So the recursion relation then is Cn by Cn minus 1 is equal to two square root of w. S is equal to L plus 1, so this becomes L plus n minus k. I am just substituting S is equal to L plus 1 in the previous expression for the recursion relation. This divided by L plus n plus 1 and L plus n minus L into L plus 1. So this is the recursion relation between the different coefficients in the expansion. Now let us look at the behavior of this series for large values of R. So the series which we have, let me just write down the series which we have again. The series which we have is U of R is equal to, there is an overall factor of R to the power of L plus 1 outside now, and then we have the sum n going from 0 to infinity Cn R to the power of n. For large R, for large values of r, it is the large values of n which are going to be dominant, because for large values of r the higher powers of r are much larger than the smaller powers of r. So for large r it is the larger values of n which will dominate. These are the ones which dominate. So let us look at the behavior of this recursion relation for large values of n, which will tell us about the large r behavior of the function u of r. So for large values of n, we can forget about all these constant coefficients, and for large value of n, what we will have left, we can also forget about the else. So what we will have for large values of n is 2 square root of w into n by n squared. So for large n, Cn by Cn minus 1, this is going to be equal to 2 square root of w by n. The numerator has 1n, the denominator has n squared, so what we have is 2w by n. So for large values of r, this is the behavior which is going to dominate. Now let us also look at another function. Let us look at the function e to the power 2 square root of omega into r. Let us expand this in a Taylor series, n going from 0 to infinity, bn r to the power of n. So how much is the ratio of bn by bn minus 1? Let us calculate this. So we know that bn for this function is 2 square root of w to the power of n by n factorial, and we have 2 square root of w n minus 1 by n minus 1 factorial. These are the expansion coefficients in e to the power 2 w r. It is this whole thing, this coefficient to the power of n divided by n factorial. So for large r, or for any value of r for that matter, for large n or for any value of n, this is exactly equal to so what does this tell us? So we see that the coefficients in this series, which is our solution, have the same relation as e to the power 2 w r, the coefficients in this series, for this function, for large values of n. So which tells us that for large values of r, our function over here for large r, u of r is going to behave as r to the power of l plus 1 e to the power 2 square root of w into r. So this is the large R behavior of this solution. So this tells us that for large R, the function g of r, this is going to be, which is defined as e to the power minus square root of w r into u of r, this goes as r to the power of l plus 1 r to the power of minus square root of w r and r to the power of 2 square root of w r, which basically is r to the power of l plus 1 e to the power square root of w r. So this function g of r cannot be normalized because it blows up, the integral will blow up at infinity. This function blows up at infinity, so this function cannot be normalized. So this cannot be normalized, so we have a problem. And what is the solution to the problem? We have encountered a similar kind of problem for the simple harmonic oscillator, and the only solution which we can have is that if the series terminates at some finite value of n and all the higher coefficients are 0, then we can have a solution which can be normalized. So if the series does not terminate, if all the terms are there, then the function cannot be normalized. But suppose the series terminates at some value of n. So this is the recursion relation between successive coefficients. If it so happens that beyond a certain coefficient, all the higher coefficients are 0. Once one of the coefficients becomes 0, all the higher ones are subsequently 0. So if one of the coefficients becomes 0, then we are saved. We can get a solution. So for the suppose the n minus 1th coefficient exists, but the nth coefficient is 0, then the condition which has to be satisfied is that the numerator over here must be 0. So if Cn minus 1 is not equal to 0, but Cn is equal to 0 and all the higher values are also 0, then the condition which has to be satisfied is 2 square root of w n plus L minus k, or this should be equal to k. If this condition is satisfied, then the numerator disappears. So we see that this puts a restriction on the values of energy which are allowed, because W, as we have defined it, is nothing but the square root of the W is nothing but the energy multiplied with these coefficients. So the square root of W is just the square root of the energy multiplied by some coefficients. So the condition for the wave function to be normalized, the condition which has to be satisfied is that W square should be equal to k square by 4. W will be equal to k squared by 4 into n plus L squared. Now let us denote n plus L. Now first of all, let us establish what are the allowed values which n can take. So n obviously cannot be 0, because at least one of the coefficients has to be non-zero. So C0, if n is 0, then C0 is going to be 0, which is obviously meaningless, right? And anyway, C0 cannot be expressed in terms of C minus 1. So n cannot be 0, n can be 1. So if if n equal to 1, this implies that C1 is equal to 0. C0 is the only non-zero coefficient. If n equal to 2, it implies that C2 is equal to 0, C0 and C1 are both not equal to 0. So it is a quadratic, it is a linear polynomial. This is just a constant. Similarly, if n equal to 3, then we will have C3 equal to 0, C2, C1 and C0 will not be equal to 0, so it is going to be a quadratic polynomial. So U will then be a quadratic linear and just a constant here. Okay, so we define n, another integer. So n, capital N is integers, L obviously can only be integers. So we define another number n, which is equal to L plus n, capital N, and n can take values 1, 2, 3, etc. So this we can now write as W is equal to k squared by 4 small n squared. Let us now put in what k is, what the W is, and get the condition for the energy. So the condition for the energy is, so W is minus 2 me by h cross square. This is equal to k squared. K is 2 me squared by 4 pi epsilon naught h cross square. This whole thing squared is k squared, this divided by 4 n squared. So this is the energy. So 2m by h cross square will, one factor of 2m by h cross square will cancel out, and this gives us E. We can label the E's. So for each value of n, there will be a different value of the energy, so we can label them by En. En is equal to minus, I have E square by 4 pi epsilon naught whole squared here I have 1 by this, one factor of 2m by h cross square gets cancelled out, so I still have one factor of 2m by h cross squared. The 2 will cancel out with the 4 here, so I have m by 2 h cross square n square. So these are the energy levels of the hydrogen atom. We can also write this in a slightly different way. So let us first do that and then go into the interpretation of this. So we can write this as minus E square by minus E square by 4 pi epsilon naught into 2 A naught. So let us identify what is A naught now. A naught, let me identify what is A naught. So let us identify what is A naught. So A naught is going to be A naught into n. So the n will come in here, n squared. So this is E square. This is like the potential. The potential is E square by 4 pi r. So when n is equal to 1, it is E square by 4 pi epsilon naught into 2 this r. A naught is some length, you can see, because if this is the energy, the potential is E square by 4 pi epsilon naught r. So this A naught is the length. A naught is called the Bohr radius. So this A naught is what is called the Bohr radius of the hydrogen atom. It's called the Bohr radius. Okay. And let us get it in terms of these coefficients which appear over here. So the coefficients which will be there, let us write it down. So there will be one factor of 4 pi epsilon, because here we have 4 pi epsilon naught squared in the denominator. So there will be 4 pi epsilon naught. The 2 is here, there will be factor of h cross squared, and then we will have m E squared. That takes care of everything, I suppose. So this is the Bohr radius, and this is the length scale we shall see, which is associated with the electron orbit in the ground state of the hydrogen atom. This is the length scale associated with that. Let me give you the numerical value of the Bohr radius. It is very important. So let me give you also the numerical value. A naught is equal to 0.529167 into 10 to the power minus 8 centimeters. So these are the energy levels of the hydrogen atom. Now there is still a little bit left. Let me finish that before closing for today. So what are the different quantum numbers that we have to describe the levels, energy levels of the hydrogen atom? So we started out with this capital N and L, and we found that the energy depends only on the sum of these two, capital N and L. So suppose you fix the value of L for fixed L, N can take all values which are greater than L, because capital N can take value 1, 2, 3, 4. So small n is L plus capital N, so it can take all values greater than N. But the energies are going to change. The energy depends only on this small n. So it is more convenient to use, instead of using capital N and L as the quantum numbers, it is convenient, it is as the numbers to specify the state of the hydrogen atom, it is convenient to use this N as a quantum number. So suppose I fix the value of N, then the energy level is fixed. For a fixed value of N, what are the values which L can take? Let us ask the question. So if I fix the sum of capital N and L, and N has to be at least 1, so L is restricted to all values less than N. So L can be any value less than N. Okay. For example, if I take N equal to the lowest value, what is the lowest value which N can take? The lowest value which N, the sum of these two, can take is 1. Okay. So suppose I have the lowest value N equal to 1. This corresponds to the only one possibility, which is L equal to 0 and capital N equal to 1. Suppose I take this case where N is equal to 2, then I have two possibilities, L equal to 0, capital N equal to 2, or L equal to 1, capital N equal to 1. N equal to 3, sorry, that's all. If N is equal to 3, then I have L equal to 0, capital N equal to 3, L equal to 1, and L equal to 2, N equal to 1, etc. The energy depends only on this value of N. So I need not specify this capital N. The capital N can be determined if I give the value of N and L. So I need not bother about the capital N. The capital N can be determined once I know L, and the capital N will only appear when I try to determine the polynomial, which is a part of the wave function. Okay. So now what do we find? We find that the energy of hydrogen atom depends only on one quantum number, only on one quantum number n. If I fix n, it doesn't fix the state, because for example for n equal to 2, I can have L equal to 0, L equal to 1, two possibilities. For L equal to 0, what are the values of m? M can be 0, here m can be minus 1, m equal to 0, m equal to 1. So these are all degenerate states. There are actually 1, 2, 3, 4 states. So a unique one wave function, to fix the wave function I have to give n, L and m. But given a value of n, L and m, I get the full wave function. But just given n, I can determine the energy. So for a fixed value of energy, we see that there are 4 possible wave functions which can give the same value of energy. Okay, so that we see that there is a degeneracy. In the next class, we shall continue with the discussion of the nature of this degeneracy.